Problem 819. Air enters an 18 centimeter diameter, 12 meter long underwater duct at 50 degrees C in 1 atmosphere at a mean velocity of 7 meters per second. It's cooled by the water outside. If the temperature is nearly equal to the water temperature at 10 degrees C, determine the exit temperature of the air and the rate of heat transfer. Okay, so let's jot down all of our givens. All right. Well, we have the average velocity. That's told to be 7 meters per second. We have the diameter, 0.18 meters. We have the length, 12 meters. We have the surface temperature of the duct. We're told that it's constant and it's equal to 10 degrees C. Okay. We also have the temperature coming in of the fluid, of the air, and that is 50 degrees C. We're given a heat transfer coefficient, 65 watts per meter squared Kelvin. We're trying to find what the exit temperature is and what the heat transfer rate is, Q dot. All right? Well, let's start. So we have air going through this duct, and we're going to need to know something about the properties of that air props. Okay? We need it to be at the bulk temperature. Well, I don't really know what the bulk temperature is. I know it's coming in at 50. I know if it were infinitely long, it would be 10. Well, I have to come up with some value that's between those two. Well, I'll say my T bulk, it's probably going to be around 30 degrees. Okay? So that helps us get some properties. Our density, 1.164 kilograms per meter cubed. My CP is 1,007 joules per kilogram Kelvin. And now I'm trying to find the exit temperature. Again, we have this constant surface temperature case. I know that the fluid temperature, the mean fluid temperature, is going to be increasing exponentially. And I have to calculate, well, let me write that equation as. The exit temperature, T sub E, is equal to the surface temperature minus Ts minus T initial exponential of negative H times the surface area divided by m dot times Cp. Okay, so far, let's see, I have H, it was given to me. I know I have the diameter of the tube. I can calculate the surface area because I have the diameter and the length. Cp is a constant. Ts I have, T inlet I have. So the only thing I don't know so far is the mass flow rate. Well, can I calculate it? Yeah, I can. My mass flow rate, m dot, is just rho times V average times the cross-sectional area. So that's equal to 1.164 times V average. I was told it was 7 meters a second times the cross-sectional area. Well, it's a 2 pi over 4 times the diameter squared. Now my mass flow rate then is equal to 0.2073 kilograms per second. The surface area, well, the surface area, I know how to calculate that. That's just pi times d, the circumference, times the length I go. So that's pi times 0.18 times 12. And this is equal to 6.786 meters squared. All right, so now I can plug into my equation. I know T at the exit, well, that's just equal to Ts, which is 10 minus 10 minus 50 times the exponential of minus H, 65, times the surface area, 6.786, divided by m dot, 0.2073, the mass flow rate, times the specific heat, 1,007. Right? So now I have everything, punch that through, and I get an exit temperature of 14.84 degrees C. All right? All right, so that's part A. Part B is just going to be